Today we're going to see how to make a measurement of gravity with the classic Lacoste-Romberg relative gravity meter. And before we can even get the meter out of its box, we need to set up its base plate to give us a nice firm place to stand it. This is easy on a hard surface because you can just stand it on its three legs. On a soft surface it's a bit more difficult, and what you really need to do is bash a hole in the surface because you want the instrument to be standing on its legs, not its middle, because it'll wobble if it's on its middle. And the base plate is perfectly robust. You can give it a good stamp to sit it into the ground and convince yourself it's firm. Now we can get the instrument out of its box. So this is the Lacoste-Romberg gravity meter, and I can't show you what's inside the box because the mechanism is very, very sensitive, and it's kept in a little oven which is at a very carefully controlled temperature. Even I've never seen inside the box. But what's inside there is essentially a mass on the end of a lever. The lever moves up and down like this. The mass is on this end, and there's a spring that pulls back on the lever, and the mass just balances the spring so it moves gently up and down. And if gravity is a bit stronger, it pulls the mass down, and if gravity is a bit weaker, the spring pulls the mass up. Now, the lever can't move very far because it's between two end stops. Most of the time it's sitting against the bottom stop or the top stop. And to make a measurement, what we're actually doing is tightening the spring or loosening it until the mass is just floating between the two end stops. So that's the principle of what's inside the box. And like I said, the actual mechanism you can't see because it has to be in its temperature controlled oven. So our first job before we take a measurement is to get the instrument perfectly horizontal. And to see whether we've done that, we have two spirit levels here and here. The dish that the instrument sits on is slightly dish-shaped, and so we can get the instrument level just by moving it left and right across the dish and watching this bubble as we do that. The trick here is to think which way you want the bubble to go and push the instrument that way. So now I want this bubble to move away from me towards the top of the picture, so I push the whole instrument in that direction. The bubble goes the way I want. It's gone too far now. Once you've got the bubbles so they're just about moving about in the spirit levels and not stuck at one end, you can finish the leveling off by turning these three screws. These two screws tilt the instrument like this, and so we look at this bubble while we're doing it. This single screw tilts the instrument like this, and so we look at this level. Am I going the right way? Yes, there we go. Now, as you can see, when you set one level, the other one goes off. So now we need to do the other levels. And watch this one. There we go. This whole process can be done very quickly by a practiced operator. If you've not done it before, it's surprisingly frustrating. With this particular gravity meter, we've got an extra aid in that here and here we have some electric levels, and these are more precise than the bubbles. So once you've got the instrument nearly level, you can finish it off using the electric levels, and those are pretty good now. So we're now ready to take a measurement. Now, the mechanism inside the gravity meter is normally kept clamped firmly so it cannot move, because it's very delicate, and if you pick the instrument up and shook it about, you would damage the mechanism. However, to take a measurement, we do of course have to unlock it. That's what this knob here is for, and we turn it anti-clockwise and keep turning, and you can feel when you've unlocked it. There we go, it won't turn any further. So that's the mechanism's now unlocked. And now we're ready to take a measurement. You'll see that there are two big silver dials on the deck of the instrument here. In any one survey, we'd only use one of those, and today we're using this one. We're leaving this one firmly locked in position. Some of these instruments only have one dial. Now, to make a measurement, what we do is we turn the dial slowly round until the mass is at the right point in between its two end stops. And we can tell when that's happened by looking at this galvanometer here that says beam on it. And when that's right in the middle, that's the right point, and we're ready to write down the answer. So I'm going to try making a measurement now, and to do that we always turn the dial clockwise. We never make a measurement turning the dial anti-clockwise. And the reason for that is to avoid any errors caused by slack in the mechanism and all the gears between the dial that you're turning and the gravity sensor. So I'm turning this dial a tenth of a turn at a time until I see any action happen. Now I can see that needle is just starting to twitch, so now I'm going to, it's gone quite a way. So now I'm going to turn it maybe a 20th of a turn at a time, and I'm going to watch that needle all the time. You can see it's gradually creeping towards the middle of the range. You can also see it's wobbling about a bit. Some days gravity is noisier than others. If there's been a big earthquake somewhere else in the world, you may just have to give up taking gravity measurements for an hour until those seismic waves have gone away. And you may just find it's generally noisy, especially if the weather's been stormy for the last few days. Because the ocean swell makes a continuous seismic noise now. I'm moving this dial even more slowly now, just one little division at a time, and then waiting in between. Now I think that's not quite there. I'll go a little bit further. And a little bit further. This does require patience. If you go too quickly, you will overshoot, and then you have to go back to the beginning and start again. Now, I think that's not too bad. The pointer's moving gently backwards and forwards across the very centre of the galvanometer. So now we can actually write down the answer. Now, to do this, the first thing we write down is the numbers in this little counter here, which looks like the mileometer on a car. And what it's counting is the number of turns of the dial from the beginning of the screw thread. Right now it says 71347, and that's 7,134 dial turns. The reason there are so many dial turns is to be able to cover all the possible range of gravity between the equator, up a mountain where it's low and you'd be at dial turn 0, and near the North Pole at sea level where gravity is much higher and you'd be up to 9 or 9,500 dial turns. So we write down 7134, which is a number of whole turns, and then we write down number of fractional turns by looking at the dial itself. The fifth digit in here, it's like the last digit on your gas meter. You never write it down. That's because it's tenths of a dial turn, and it's better to read the tenths off the dial itself. And you can see that's 4 tenths, 5 tenths, 6 tenths. So this is between 0.6 and 0.7 dial turns. To get the next digit, we count these little divisions. So this is 0.65, because that pointer is very near that 5. And we estimate a third digit by estimating how many tenths of these tiny divisions we're at. Now, as it happens right now, the pointer is dead on one of those divisions, so I would write the answer down as 7134.650. That answer then goes into the notebook for the day, and we would always at a station make 2 more measurements to convince ourselves we got it right. To make a second measurement, we would turn the dial back a turn, turn it forward nearly a turn, and then we would repeat the whole process. You can do the second and third measurements much more quickly because you know approximately where the answer is going to be. So I'm not going to complete the second measurement, but if I was desperately actually trying to get a measurement at this point, I would do 3 measurements, and if they were all roughly the same, I'd be happy. I'd go to the next station. If I had 2 that were similar and 1 that was different, I'd assume I'd made a mistake on that one, and I would then repeat the measurement until I'd got 3 consistent measurements. When you're happy with your measurements at a station, the instrument goes back in its box, but before moving it, you must always lock down the mechanism by turning the locking nut fully clockwise. And you can see when I did that, the beam galvanometer moved over to the right-hand end. When we took a measurement just now, we did it by looking at this little galvanometer. But not all of these instruments have a galvanometer on them, and you have to take the measurement in the old-fashioned way by looking down this eyepiece. And what you see when you look down the eyepiece is a little graticule with a black cursor moving across it. That cursor is actually a line marked on the gravity sensing mechanism itself. So by making a measurement like this, you're making it very directly with no electrical things to go wrong between you and the gravity sensor. I'm going to put my mobile phone camera on top of the eyepiece, and I will attempt to show you what you see as you look down the eyepiece. There we go. So there's a little graticule scale, and that big fat black line will move across the scale as you adjust the dial, exactly like the galvanometer does. And to make a measurement, you need to adjust it to exactly the right position, which for this instrument is 2.4 on this scale, and it tells you that on the notice on the surface of the instrument. And that's actually just about right now, because you read the cursor from its left side edge. So 2.4 means the cursor exactly fills the space between 2.4 and 2.5 on that scale. Every instrument's different in this respect. You can see this one, it says reading line 2.4 here. A different instrument might say reading line 2.7. So we've measured the gravity, but gravity data are no use unless you know how high your stations are with respect to each other. And to measure that, we can use this traditional levelling equipment. One part of the equipment is the surveying pole, which is like a ruler, except it extends out to being 4 metres tall. And you can see it's marked in very big numbers so that you can see them from a distance. That 8 is 0.8 metres, that N is 0.9 metres, big red one for 1 metre, and then the red one and the black one means 1.1 metre, 1.2 metres, and so on. We read the exact values from the top of these little black bars. So the top of this black bar is 1.1 metres, and the top of this black bar with the pointy end is 1.15 metres. Now, on a normal day, you would have an assistant and have them stand the pole on the station and hold it exactly vertically. If you're lucky, you've got a pole with a spirit level on the back so that you can tell you're holding it vertically. Today, because I don't have an assistant apart from my camera operator, I'm going to use this tree to hold the pole up. We'll pretend that the station is at the bottom of the tree, and I'll show you how we make the actual height measurement. The measurement is made with a special little telescope which we put on this tripod. The thing that's special about the telescope is that it looks exactly horizontally. The process of levelling the instrument is actually rather frustrating for a beginner. First you have to adjust the tripod so that the top of it is quite close to level, and that's the hard bit. Next you finish off the levelling with these 3 screws, and that's very similar to the 3 screws that we use to level the gravity meter. And you can tell you've got it approximately level because there's a little spirit level on top of it here. So I'm now going to turn these screws in an attempt to get that bubble to come to the centre of the level. This also is a process which can be very frustrating. It's particularly frustrating if you're a long way off level and people don't know which way to turn the screws. Once you've got the bubble moving about in the middle of the level like it is now, you'll probably be able to level it fairly quickly. There we go, the bubble's just about perfectly in the centre of that circle, and now we're ready to take a measurement. Now, the spirit level isn't the whole story, because inside the instrument, the light, as it passes through the optical chain, goes through a prism which is hung like a pendulum. And the fact that that pendulum can swing backwards and forwards means that as long as you've got the instrument approximately level, the way the light passes through the pendulum compensates for any slight error you've made in levelling and ensures that the direction you're looking is exactly level. Now, we point the instrument at the surveying pole and look through the eyepiece. Get the scene in focus. And the tricky thing here is that you want to look at the horizontal crosshair, and the trap that many people fall into is that in addition to the big long horizontal crosshair, there's a short one above it and below it. And it's far too easy to read off one of the 2 short crosshairs instead of the long one in the middle, and you'll get an answer that's wrong by about 10 centimetres, which won't do. What I'm going to do now is attempt to show you what you see looking through the eyepiece of the instrument. There we go. Oops. There. Now, the camera will probably autofocus itself in a minute. Go on, get on with it, you. There we go. And you can just see there the crosshair a little bit below the red 1 metre number. It's a bit difficult to hold this steady enough, but you get the general idea. It's much easier to see what's going on when you're looking through the telescope with your own eye. Reading off the long crosshair, I can read this, and it looks to me as though it reads right now 0.9567 0.975 metres. That number on its own means nothing. The important thing that we do next is take the surveying pole, move it to the next station along, and without disturbing the surveying level, we read off from the surveying pole at the 2nd station. And the difference between those 2 numbers that we've read off is the difference in height between those 2 stations. We repeat that process between every pair of stations, and now we know the height of every one of our stations with respect to our starting point. And if you're serious about this, you go up to the end of the line of your stations, and then you turn around and you come back and do it all again so that you've got a check and you know that you've done it correctly.